So the videos that you're about to see, so the videos you just watched were ones I made last year. So now I'm adding more in just to kind of give some clarification and to continue on into diving into quantum. Okay, so I just talked about the Schrodinger equation. You've got the kinetic energy, potential energy, yielding the eigenvalue equation of the energy. And so this part here, both of these, if you dissociate or associate out or factor out the wave function, you'll have minus h bar squared over 2md squared dx squared plus the potential, that all operating on your wave function. This is your Hamiltonian. Okay, so I'm going to start then with your Hamiltonian. And so again, the wave function is contains all the information on the system, and we're going to go ask it a question, and we're going to say, hey, wave function, what's your total energy? And it's going to spit out the energy. Remember, we want a way to get discretized or specific quantized energy states. In thermodynamics, for those of you who just went through thermodynamics with me, we did all of this work with continuous functions. For those of you to pursue thermodynamics with me next year, guess what? We're going to do all these continuous functions where you can take integrals because they're continuous. Here you can't, kind of, because these are discrete energy levels. Energy's here, 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 or here, not in between. Okay, so in 1926, Max Born, who was working with Niels Bohr at the Copenhagen Institute, postulated a few things. Actually, I'm just going to rewrite the Schrodinger equation. From here on out, you'll most likely only see me do this. H psi equals E psi. It's a beautiful equation. So in 1926, Max Born suggested, number one, if psi of x is real, it is a real number, no complex numbers, okay? It is a real value. Number two, psi of x squared times a volume is equal to the probability of finding the electron. All right. And what that means is that here, and I'm just going to give you a wave function. So if this is x equals 0, and then this is your psi of x. So this is the x-axis. So this is x equals 0. This is x equals some number. At some distance away, here's your wave function. Psi squared would look like this. So if you squared the negative sign, and actually it would probably be a lot higher. There you go. So if you square this number, it's going to be bigger. And if you square this negative number, it's going to be bigger, and they're the same value. So it's going to look like two bumps. Okay. So in one dimension, so psi squared, so this is psi squared, times the volume is equal to the probability. Okay. So psi of x squared multiplied by an extra dimension. And in most cases, we say volume, but for one dimension, what is a volume? It's just a distance, okay? Because 3-dimension is length, width, and height, okay? For one dimension, we're just going to look at length. So for 1D, we've got this times length, which means psi squared times some dx. This is an infinitesimal length, but I want to have a bunch of them. So I'm going to integrate. And so I'm going to basically take, if here is my wave function, I'm going to take this small dx. So this is x, here's psi squared. So this is dx. So some psi value here times dx. I'm going to take that volume. Okay. So that is equal to the probability of finding the electron. Okay. And now if I, oops. Okay. Now if I take the sum of all probabilities, so this is number 2, number 3, if I sum all probabilities, then that means I'm going to find the particle. Okay, so that means if I sum, which means I'm going to add up all of these slices, and I integrate or add up all of the different, this is a Riemann sum then I'm going to add up all of the psi squareds times, so psi squared times dx, I'm going to add them all up. Then that means I'm going to take the integral of psi squared dx, that's going to equal 1, because that means 100% that I'm going to find the particle. So equals 100% find electron. Okay. Now, if I plot psi squared versus x, so this is number 4. If I plot psi squared versus x, I get a probability distribution. Okay. Now, all of this is important because I need you to know these things, because we are going to, over the next 3 videos, I think, maybe 2 videos, I'm not sure, we're going to dive into each one of these. Okay, so there are these set restrictions on how we can use the wave function. Can it have what's called a superposition? What is orthogonality? How does Heisenberg uncertainty principle play in? All of those things we're going to build onto, or scaffold onto, a foundation, and that foundation are the postulates that Max Born presented in 1926 based on Schrodinger's wave mechanics. Okay, where the wave mechanics, or the wave, comes from the wave function, which Schrodinger defined. Okay, so number 1, psi is real, no complex numbers. Number 2, psi squared times a volume equals the probability of finding the electron. Okay, there's a probability, and then there's a probability density. Or actually, I should say, this becomes, psi squared becomes probability density. So probability, so density is mass over volume. This is actually a great way to look at it. Let me get rid of this. So this is called probability density. Probability density, which you can think of as the probability per volume. Instead of mass density, it's probability density. So it's probability per volume multiplied by your volume that you've got. That equals your probability. Okay, probability density times volume equals probability of finding the electron. Number 3, you're going to sum up all the probabilities, which is essentially multiplying it by your volume and then adding all those together. And then number 4, you're going to plot that psi squared, your probability density, as a function of x, which is going to give you your probability distribution. Cool? When we finally get psi squared built, that's going to give us the shape of the orbitals. And the size that give us the actual hydrogenic atom orbitals, way complicated, but it's beautiful in its elegance. So that's what we're building towards. Go team!